Okay. So, sorry. So almost all the basics required for this course are already covered. So and from today, I'll start the actual content, that is the important research areas of cache memory. So today's class will discuss at least two three important areas or areas of cache memory where recent research is going on. But we'll not go in more detail today, and from tomorrow we'll pick one by one each of this research area, and we'll spend at least 1 week on each topic. Okay. So again, when I'll discuss about the recent research area, there will be some basics I have to clear again, but those basics I think is already known to you. So here I'm discussing about cache replacement. We all know about the cache replacement. What is called cache replacement? So to understand it, let me consider that this is a set associative cache where there are multiple sets involved. Okay, and these are the ways, right? So the properties of set associative cache is known to you. Mapping on set and all is known to you. So cache replacement policy means if the set is full, suppose A, B, C, D, E, F, if the set is full and you want to place a new block in this set, then you have to replace a old block. That is called replacement policy. So any replacement policy has three modules: insertion, promotion, and eviction. Insertion means where you have to place a block when you are first time you are fetching a block. Suppose this is the scenario, and in this scenario you want to fetch a block Z in the cache, which is also mapping to the same set. So what you will do, first you will go to memory and you will fetch the block. But when you will fetch the block first time, when you will insert the block in the set, in which position you will insert? In LRU replacement policy, when a new block is inserted, we place it in the MRU position, right? So insertion means where what is the position as per the replacement policy when you are inserting a block first time. Promotion means if there is a block in cache, suppose at this moment if there is a request for block A, then that request will be hit in the cache, L2 cache, right? So if there is a hit in the cache, then how you will promote the block? So normally in LRU replacement policy, if there is a hit in a block, then we can make this block as a MRU block. Okay, because the most recently accessed block it is. So this is called promotion policy, how you are promoting a block. And eviction policy means which block you have to select as a victim block. Victim block means the block which you will remove. So you have to remember this term, what is called victim block. The moment I say victim block means the block that will replace from the set to place another block in the set. So insertion, promotion, and eviction are very important. One more concept is important to understand. Suppose the same for each set, the hardware maintains a separate hardware unit for maintaining the replacement. So suppose A, B, C, D, E, F. There will be a separate hardware unit like this where this LRU position will be maintained. So suppose LRU positions are maintained like this. Let us assume that this side it is LRU, this side it is MRU. So it may be possible that at this moment, if A is being accessed again, then what will happen? A suppose this is the current situation, and the core is requesting for A, then A will be accessed again. So one if the A block will be accessed again, then A will become MRU. So its position say it will remove from this position, and we have to add it in the MRU position here, right? So you can understand that this is the LRU position and this is the actual physical set. In actual physical set, there won't be any change of block because previously A was in the LRU position. There was a access. Based on this access, we move the block from LRU to MRU, but that moving is only in the hardware means replacement unit, not in the real set. So whenever we'll discuss research paper, most of many time we'll say that if there is a promotion, then we'll move the block from LRU to MRU. Don't think that the block is moving in the set. Block is remained in the same position in the set. Only we change the replacement policy. Now the next question is how will change the replacement policy? Is it true that in replacement policy there is a separate hardware, or in that hardware initially the A was here and then we'll move A from here to here? No, that is also not. This is a logical thinking, because if we think like this, then we'll move it from LRU to MRU. then actually it is easy to understand. But in reality, what we will do here, we will just change the values, right? Suppose how will maintain this change? Initially a was here, a was not here, suppose, right? Initially at that time, how we maintain? So actually in hardware, one way is we maintain the age or maintain the last access time. So this is a logical, this is not in actual hardware. What we will do, will maintain the last access time of this, last access time of this, all this. Suppose these are the last access time of all the blocks. So in this case, 100 is the oldest one. Last access time, suppose assume that 100 is the oldest one. So now if 100, if you want to become a as LRU, then we'll just simply change this value from 100 to 0, suppose. So that thing actually happens. So when we'll discuss about replacement policy, we'll discuss many times. We'll say when moving a block from LRU to MRU, MRU से LRU में जा रहा है. लेकिन initially you have to, means internally you have to understand that we somehow we are changing the values to maintain this. And one more thing is, each this replacement hardware is separate. Means it may be embedded within the set also, but it's the independent hardware unit. I hope all this thing is clear. So, for suppose there is a, how many ways are there? One, two, three, four, five, six. Six तो होता नहीं है, normally eight होता है. Suppose there are eight-way associative set. So if there is a eight-way associative set, and for example, if you want to maintain a LRU replacement policy, then what we normally do is, we normally suppose how there are eight ways, right? Eight ways. So if you want to maintain the age bit of each set, each way, then how many unique combination is possible? There is eight unique combination is possible. So maybe you can say that 000 is my LRU, and 111 means MRU, and there will be some other intermediate blocks here, right? So it means that to maintain LRU replacement policy in each set, you need, here if they set it as a to a, then you need 3 bit per block. So 000 will be the for the oldest one, and 111 for the newest, the most MRU block, or you can consider the reverse also. So in that case, you can see you no need to store the age, and obviously storing the last access time is not practical. In simulator we do that, but in real hardware, storing time means it will take huge data, right? At least 4 byte of information is required instead of 3 bit, because as timestamp is normally almost equivalent to an integer value, right? So 4 byte will be required. So instead here we are using 3 bytes. Why we are not using timestamp? Because if we use 4 byte for one counter, then your storage, extra storage overhead will be more. So that is called as hardware overhead. So whenever you are designing anything in hardware, we have to consider this also. It's not just that you are improving performance, and we will discuss these points throughout this course. That it's, whenever you are proposing a new idea, suppose you are proposing a magic replacement policy which is improving the performance, improving the CPI, but if it is increasing the storage overhead by 100%, then it's not a good idea. That's why we have to think in this direction also. So you can see we are using 3 bits, and after few lectures you will find that even 3 bit may be more if your cache is more larger. So I hope the basic concept is clear. If why I'm spending time on it, because some of you maybe think like in this way that LRU to moving LRU to MRU means we are moving the physical block from one position to another. No, that is not true. Also, we are just change the position in logically. Okay. So now important term. There are some important. So LRU replacement policy is done. You already know LRU replacement policy. Now, in LRU replacement policy, what we normally do is, suppose you have this block A, B, C, D, E, F. Suppose this is LRU and this is MRU. So now in this scenario, if a new block Z arrives, then how we'll place it? We'll simply remove this block, because this is LRU block. So we'll remove this block, okay, and we'll place Z here. So in real set, what will happen? This A will be removed, Z will be placed here, but Z is actually, it is an incoming block. So in LRU, the insertion policy says place it in MRU, right? Place in the MRU position. So Z will be placed here in MRU position. So see the difference. In actual set, it placed in by replacing Z, replacing A, but here we place it in MRU position according to insertion policy. right? So now after this request, assume that initially the core one was requesting for Z, but assume that after this request no core has requested for Z after that. So if you know that at this moment if Z is requesting, but after this moment no one else will request Z anymore, but still you cannot replace it, because if this is currently now the block is MRU, this block will be only replaced when gradually this block will be moved from MRU to LRU. When it will move from MRU to LRU, all these blocks will be either replaced or maybe accessed once again, so that it can be promoted from this position to somewhere this position, right? So it means that in LRU replacement policy, if you move a block in cache, then it takes some time to replace it. And at that time, if the block is not accessing, we call such blocks as dead blocks. So in the actual definition of dead block is, if there is a block exist in cache, this is the block exist in cache, which at this moment we'll call it dead. If from this moment to future, this block will never access by any code before until its eviction. Means from this moment, suppose this is the current moment, from this moment to suppose at this moment it will evict from the cache. In this duration, this block will never access again by the core. If this is true, then that block is called that block. And why we call that block? Because this block is unnecessarily wasting the space of cache. There is no point. यहाँ से इसको एक बार एक्सेस करने के बाद इसको डिलीट भी कर सकते थे हम लोग, राइट? बिकॉज देयर इज नो पॉइंट टू कीप इट ऑन द कैश. बट इफ वी सिंपली गो follow the eviction policy of LRU, then LRU eviction policy is always select the LRU block, the oldest block, and Z is just recently came, so you cannot replace, though it is a dead block. So that's why the limitation of LRU is clear, and it's a huge research area. People are still working on it, that how to remove the dead block. So removing dead block is not an issue. You can remove it, but the question here is how to detect a dead block. Because here I'm saying this is the current time. At this moment, this is the current moment, or ये future है. At this standing at this moment, how can you say detect the future? You cannot detect the future with 100% accuracy, right? So that's why here the magic of predictions came. So who can give better prediction mechanism, that prediction mechanism will give you more accurate results. Means जितना ज़्यादा आपका prediction accurate होगा, उतना ज़्यादा dead block detection भी correct होगा, right? So there are a lot of what's going on dead block prediction, not detection. As I said, because no one knows the future, you cannot detect it with 100% accuracy. But there are a lot of predictions are there where based on those the people predict that okay, this may be the dead block. So instead of replacing the LRU, remove that block, because maybe LRU will be accessed again, but this is a dead block that will not be accessed again. So remove that block. So those blocks are called dead block. I hope you are understanding it, because the concept of dead block will be required in future also. Just one moment. Uh, just one moment. Okay, so dead block done. Then scanning application. Scanning application are also they are the main contributor of dead blocks. Scanning application means that if there is it's like a live match going on. Suppose if in YouTube you are watching a live match. So if you are watching a live match, means every data that is coming is a new data. And after means watching it once, that data is deleted, right? Every time you are getting a new data. So that is called scanning in time. Suppose there is an application running in this core, and that application every time it is requesting for a new data. So it means that it is not getting benefit from two type of principle of locality, at least not from temporal locality. Maybe it will get some benefit from spatial locality, but not from temporal locality. It means every time it is requesting for a new data. So that those type of applications are called scanning application, and sometimes we also call them streaming application, like live streaming application, live streaming. So from there, so uh, why I say that they are not getting a benefit from temporal, but maybe they will get benefit from spatial locality. This is because when suppose this application is requesting for a block called A1, then when it will go for A1 to main memory, it will bring a chunk of block, right? That is a chunk of data, that is called block. ब्लॉक में A1 भी रहेगा, B A1 A2 AN तक रहेगा. So after that, if it will request for A1 to A2 to AN, then those will be hit here because of spatial locality. But here I'm saying it will not repeat any block. So it will not repeat any block means A2 will not be accessed again. So temporal locality use नहीं हो रहा है. So after that, it will request for a new block. So it means that once it is requesting for a block, it is not accessing the block again. It means it is becoming a dead block. So that's why I say scanning applications are the main source of a dead block. So that part we have to understand, that which one is called a dead block here. Just 1 minute. Yeah. Okay. So dead block done, scanning application done, then thrashing application. Thrashing application means suppose this I'll explain it in this way. Suppose these are the access request of a thrashing application A to AM. So this number of blocks here is more than the associativity. Suppose the associativity here is 8. Associativity here is, this is A to A. There are 8 associativities are here. And okay, one more important point, and I'm assuming that we are targeting a particular set. So I'm only discussing about associativity. Maybe some of you will think that there are a lot of set. Which set it will go? So whatever discussion I'm doing here, I'm assuming that all the sets are going for all the blocks are going to a particular set. So if you consider about multiple sets, that is also true. But to make this explanation simple, I'm considering only a particular set. So suppose there is an application where the access sequence are this for a particular set. So let me add set here. So suppose for a particular set number 1. So now these number of blocks here is more than the associativity. Suppose associativity is 8, but here suppose the number of blocks are 30. And there is a loop here. Means these request is moving. So it means that this application is satisfying temporal locality and spatial locality both. Spatial locality to kaise ho raha hai? It is, I have just explained. Temporal locality, how it is maintaining, because there is a loop. So if you are requesting this block here, then it is sure that in future again this block will be requested. But see your cache support. Your cache has only 8 ways. So even after this application has repeating behavior, but your cache will not get benefit from it because of limited number of ways, because there will be, after this first 8 blocks, your cache set will be full. So to access the next 8 block, you have to first remove the first 8 block, and then you have to load the next 8 blocks, right? So it means that even when the next time when you will access this block, that block will be a miss in cache, though there is a repetition. So instead of this, if you assume that instead of 8 ways, if your cache has, instead of 8 ways, has 50 ways, then there will be no misses, right? So when next time we'll go for a request of A, then though that A could have be a hit in the cache, but that is not the scenario here. There is only 8 ways, and since there is 8 ways, this type of application is called thrashing application. Why thrashing? Because there is repetition, but that repetition is not getting benefit because of the limited cache size. But you have to understand there is a difference between thrashing and scanning. Agar scanning application hai to scan, it is not depend on the cache size also. Even if there are 50 ways, if you are running a scanning application, then also there will be a lot of dead blocks, right? But that is not true for thrashing application. So you should remember what is called scanning application, what is called thrashing application. So these definition will be, you will again see this definition when we'll discuss when we'll discuss the research paper. So but at least at this moment, you should know this whatever I'm explaining, such that when you start under explaining research paper, it will be easy for you to study. So in any point, if you think that sir is not writing the definition of any of this, so don't worry. When you will start reading the research paper, All these terms will be mentioned there. Then security issues that I am not discussing now. I'll discussing at the end today. Security issues. This is the term first time I'm introducing in this course. Security issues. So maybe quickly I'll tell you what the security issues means. So when all this replacement policy and everything that we'll discuss here that has been proposed. So what people are trying to do at the beginning? People are trying to do that. Okay, suppose LRU policy was there, but if there is a dead block, so how to handle the dead block? How to predict the dead block. But when they propose all this prediction and all, what the important thing they assume is they assume that all the applications that are running in the core are innocent. Or maybe they assume this also, that all the application that is running on the computer, they have no idea about what is the internal replacement policy going on, what are the set mapping and all. They have no idea, like all these things were assumed. But suppose you at today's world, you have to understand that there will be a smart person who are using the computer. He knows that what is the mapping policy of the cache, what are the exact structure of the cache, and what is the internal replacement policy going on the cache. So if a person knows all these things, is it possible for that person to write a particular application such that that application will purposefully request for some blocks in such a way that it can create a performance issue or performance degradation in the code? For example, in LRU, suppose a person know that okay, this machine has LRU replacement policy for its cache, so let us design a scanning application. So what this person will do, this person will write a scanning application. How it can write a scanning application? Very easy. In just few lines of C programming, you can write a scanning application. That we'll discuss. Maybe first you will go for a malloc, and by malloc you will reserve a huge memory space, and from this memory space what you will do, in this memory space you will request in such a way that every time there is a miss in the cache. So either you can design a scanning or tracing application. If you know that it's a to a set associative cache, then maybe an attacker can purposefully design a tracing application. So if suppose there are four cores in the computer, in one core very important application is running on. Suppose very important application is running on, but in another other cores, no, the other three cores. Suppose there are attackers which are trying to run either scanning and threshing application. So इससे क्या होगा? The performance of the important application will also go down. So in this course, what we'll try to do this time, this time I'm giving a new angle here. Every replacement policy, every technique that we'll discuss in this course, try to find out a security issue. I mean, or you can also say this is a DOS attack. DOS attack, maybe you know from the network paper, right? Also the our actual network course means that we do in our BTech also. DOS attack means denial of service attack. So performance issue means there will be application who will do something which can degrade the performance of the entire cache. And for this, no suspicious hardware component is required. The application will only know the property or behavior of the cache or behavior of the memory, and just understanding the behavior of memory, it will misuse those properties. So we'll give a close angle on these security issues, everything that we'll study in this course. Okay, so now issues with the means replacement policy, LRU replacement policy. Dead block is one of the main issue of means existing LRU replacement policy. Why I am spending a lot of time on LRU replacement policy? Because whatever replacement policy even today we'll discuss, even today people propose, they somehow depend on LRU. They are related with LRU. That's why I'm discussing LRU here. Less effective in LLC. Less effective in LLC means, let me give you one term here. I'll say that the principle of locality, I think it is clear to you. So the main property or the main benefits of principle of locality is consumed by the higher level of caches. So here, what are the higher level of caches? L1 is the higher level of caches. So the main benefit of the principle of locality, the temporal and spatial, these are consumed by the higher level of caches. Like this will be consumed by L1. So in L2, those properties are not getting much benefit. So why I'm saying this? Because suppose there is a block called there is a block, and now instead of what I'll say block here. Suppose there is a block here. Block is called A. So that block is first time we will move the block from main memory to L2, and from L2 to L1, and then L1, from L1 core is accessing. Suppose it's not a dead block. Core is requesting for this block for multiple times, but in a very short duration, like this. Okay, so maybe all these requests, maybe here there are so many requests, maybe all these requests will be hit in L1, isn't it? All these requests will be hit in L1 because all these requests are in small duration. So it means that the temporal locality is getting benefit in temporal locality is benefited in L1 cache. But see, after this maybe there is no more access. So in this case, you cannot say that at this moment you cannot say that A is dead. No, it's not that. It is requesting, but all the requests are served by the L1 cache. There is it is getting hit in L1. It is not getting replaced from L1. So इसका मतलब यह है कि in L2 it is accessed only one, though it has repeated behavior. It means that that's why I said that the main property or the main benefit of principle of locality is consumed by the upper level of cache. Imagine that if there is two more level of caches between L1 and L2, so all this upper level of cache will get benefit of principle of locality first, and then in last level cache it get less benefit. So that's why when a last level cache is getting less benefit from principle of locality, it means that the dead block will be also more in last level cache. So if dead block is more, then how to handle it? So that's why maybe the LRU replacement policy is good for L1 caches, but not for last level caches. That's so. And for the even today, most of the modern processors, they don't do much experiment with L1 cache. Maybe even today's replacement means processor use the LRU replacement policy for their L1 caches. But a lot of experiment is going on for last level caches, and in me these course mainly will discuss those only. Okay, so this part is done, but maybe I have to explain optimal replacement policy also, because this is one of the most important replacement policy. Why I'm saying this is most important replacement policy, because all the replacement policies are try to compare with this replacement. What is optimal replacement policy? I think it is well known. We already know it from the course of operating system also. Optimal replacement policy says that as every time you select a victim block means the block which we need to evict, right? So every time we select a victim block which will be used in the farthest future. So suppose this is the current time, and there is a block A will be accessed here, block B will be accessed here, and block C will be accessed here. So which we have to take as a victim out of these three? We'll take C as a victim, because it is saying that take the block as a victim which will be used in the farthest future. So B and A are not using in farthest future, because C is using in the farthest future. So let us take C. So that is called optimal replacement policy. But again, you can see from this definition only that it is a theoretical replacement policy. In real machine, it is not possible to implement. Why? Because no one knows future. Sitting at this time, this is your current situation. You are at this moment now. How can you predict the future? That in future, which one will be accessed at which time? So that's why optimal replacement policy is not possible to implement in a physical machine, but that gives the best result. So even today, almost all the recent replacement policy also has a gap between optimal replacement policies, and that's why people are still working on replacement policy to reduce the gap. So if you compare with LRU, maybe the gap will be more than 70%. So you can understand that's why people are still working on replacement policies, though it is a very simple idea, but still people are working on it. Yeah, I think one more point here is also sometimes the optimal replacement policy is also called Bilard's replacement policy. So either in this course, I'll use the term called Bilard's replacement policy or optimal replacement policy. And again, as I say, most of the time that we will discuss about the LRU LLC based replacement policies. The modification or the improvement in replacement policy that we'll discuss, those will be mainly for last level caches. So only one point I will discuss here, and then I'll move forward. And that point is, if I am saying that the optimal replacement policy is not possible to implement, then how people are comparing the performance of other replacement policy with this optimal replacement policy? So this is a question, right? That question can be answered, and that question can be answered because if you have a trace based simulator, then we'll answer this. So I think I will answer this question after 2 3 lectures when I'll discuss about trace based simulator. Basically, if you know the history completely means and then you can go forward and check the history. So there are two types of simulator we will use. One is called full system simulator, and another is trace based simulator. So the champ sim simulator that you will use for your term papers and assignment, that is a trace based simulator. So if you know the trace, you know the future also. So in that way, you can implement optimal replacement policy in simulators, not in real machine. So we'll discuss this after 2 3 lectures. So I'm skipping it from now. So I from here. So I hope you are getting some idea about replacement policy and their challenges, and why people are still working on replacement policies. Then there is the next concept called cache partitioning. What is called cache partitioning? So suppose there are two core here. You can see each core has their L1 cache here, and L1 cache is also set associative, and L2 cache is also set associative. L2 is also considered as LLC, last level cache. So it may be possible that there is two application, there is A1 and suppose A2, two applications are running on. It may be possible that the application A1 needs less memory space and A2 needs more memory space. So if you just simply depend on the LRU replacement policy here, then it may be possible that it will give equal importance to both. Or it may be also possible that out of these two, maybe A1 and A2, A1 is running a scanning application. So if you just depend on LRU, then this A1 only will take the entire cache space because it's a scanning application or a thrashing application. In that case, maybe your A1, A2 needs less space, less cache space, but it's a cache friendly application. Cache friendly application means it's not scanning, not thrashing, means it follows the principle of locality. Means if there is a request of a block in from A2, then it will be again hit in the cache. So it's a cache friendly application. But if there is a scanning application running in another core, so that application, it may be possible that all the space will be consumed by that application. So to handle this, a concept is used in shared cache. Shared cache means this last level cache is shared among all the cores. So a concept is called cache partitioning. So partition the cache among the cores. So maybe this is the partition, suppose. So in that case, this partition is called way partitioning. Why way partition? Means we'll give the only these two ways to A1 and remaining ways will give to A2. Okay. So in that case, if A2 need more space, A2 is getting more space. Even if A1 is a scanning application or a attacker has designed a scanning application, that application cannot degrade the performance of the complete cache because it cannot place its data outside this partition. Okay, so that is called cache partition. So these two terms, I think I have already explained. What is called shared case, unified shared case kya hai, I have already explained. Distributed shared case means nuka and tcmp, all these things I have already explained, so I'm not repeating them here. But you should know the term, what is called shared cache, what is called nuka, what is called tcmp, what is llc. I'll use this term many times in this course, and I'll assume that you know the low level idea concept from this also. These four terms are very important: nuka, tcmp, then llc, ये सब क्या है, right? Then shared cache, all this concept, I'll just use this term, and you have to understand the internal meaning of this term. So if any point I think is not clear, please watch the previous video and try to clear these concepts. So cache partitioning, I have explained the basic idea of cache partitioning. There are two types of cache partitioning: static and dynamic. Static partitioning means you fix the partition during the boot time of the computer and let the partition say as it is until the computer terminates. Means when the computer will executes, there will be no change in partition. That is called static partition. And dynamic partition means the partition will change during the execution. So why static partitioning is not effective solution? Because it may be possible that if a application is running, then it may be possible that the demand of the application may change dynamically. Suppose at this moment A2 needs more space, A1 need less space, but after some time it may be possible that A2 need less space and A1 need more space. At this moment, if it is a static partitioning, then you cannot change the partition and performance will degrade. So dynamic partitioning means dynamically it will observe the behavior of each application that is running in the course, and then based on this, the partition will change dynamically after a fixed cycle, fixed period. So suppose at this moment there is a partition change happened, and the partition is currently this. Then maybe after this is the period. After this period, it will again change the check the behavior of application, and based on this behavior, maybe the partition will change from this position to this position. Okay, so now this entire part will be accessed by A1, and only this part will be accessed by A2, and this will be repeated. So static partitioning and dynamic partitioning is clear. Way partitioning and set partitioning. Way partitioning, the partitioning that I've explained here, they are those are way partitioning. Why way partitioning? It is dividing the ways. Means see at this moment all these ways are for A1 and these ways are for A2, right? So I have not said anything about set. It means that whatever partitioning I have done here, it is true for all the set. So that's why these are called way based partitioning. Then there is some recent partitioning also possible, and set based partitioning means give this sets to A1 and remaining sets to A2. This will be for A1 and remaining set for A2. But you can see there is a difference. If we go for way based partitioning, there is no change in mapping, because according to set index you can still map to a block to a particular set. But if we go for set partitioning, then set index mapping based on set index is not correct. Suppose there is the application in A1, based on set index mapping, it is mapping to this set, last set. But ये last set तो अभी A2 को दे दिया है हमने, right? So in that case, I think there will be no space for that block. So it means that if we go for set partitioning, then we need to change the mapping policy also. So all these things we'll discuss in this course when we'll discuss about cache partitioning. So challenges in cache partitioning. If cache partitioning is so easy, then why we'll discuss in this course? First is how to record the application behavior. Static partitioning का कोई problem नहीं है. You can go for static partitioning directly. Boot time पे एक partition fix कर लो, continue with it. But you know, as I said, static partitioning is not a solution. It degrades the performance of the computer. So if you want to go with dynamic partitioning, then all the challenges will arise. First, how you will record the behavior of cache applications. Based on the behavior of application, you will change the partitioning. It is easy to say, but actually how you will record those behavior, it's a challenging task. So we'll discuss about this. The overhead of training unit. Obviously there will be a training unit who will train, who will observe that the what should be the next partition. So there will be some hardware overhead of it. And maintaining fairness. So when you are partitioning the cache among applications, how you have to ensure that the partitioning algorithm is fairly dividing or fairly partitioning the cache among all the applications. So all these things we'll discuss. So these are the challenges, and that's why people are still working on partitioning, cache partitioning. And one more thing is recently adding on top of it is security. Security means you can understand here now. What about if there is a suppose there is a dynamic partitioning happening on it, and the logic based on who is the partition is changing, that logic is known to a attacker. Obviously it may be possible, right? Suppose I am the manufacturer of a processor, but maybe lot of employees who works under me, then some employee may leak the internal application that okay, these are the policy based on which partition changes. So what a attacker can do, attacker can first try to do access some blocks such that those logic will be targeted, and based on those logic, first it will change the partition purposefully. So if it can change the partition, maybe it can degrade the performance. So suppose A1 need very less partition, very less memory in the cache, but A1 is an attacker application. Somehow if we know the logic, and it will if it can do something such that it can move the partition from this position to this position, then all this will be available to A1 and A2 के पास बहुत कम रहेगा. तो इससे क्या होगा, it will degrade the performance. That's why I'll say from this year we'll try to give a security angle to everything. So when they design all this application, at that time people didn't think about the security issues, because at that time they assumed that the application that will run will be innocent. The people who will use those applications, they will not have idea about the internal hardware mechanism, but that is not true. So today, if we even we design, if we propose the partitioning algorithm, we have to think this concept also, that what about the DOS attack? अगर मैंने partitioning algorithm बना भी दिया, is it possible that if some attacker is there who can attack this code, and it can purposefully change the partition to reduce the performance? So all these things will also think. There is one more security angle that I will not discuss in this course, because there is a security course in parallel going on, and it is taken by Dr. Kalyan. So I'm here just saying about DOS attack. DOS attack means there is no correctness issue, or it will only overload the means computer, means it will degrade the performance. आपका काम और आपका application ठीक ठाक ही run होगा, that execution will be correct, but it will be delayed. That's why it's called DOS attack. There are some more attacks are there where people try to extract the important information. If there is the encryption important application going on, then maybe they can extract the encryption key. So information leakage is also possible. through hardware security hardware issues, but that will not discuss in this course. Here in this course, we will only target about the DOS attacks. So cache partitioning का basic concept मैंने बता दिया. Prefetching is another concept. I think this also you know. Prefetching means if you are requesting for a particular block, suppose C1 is requesting for a block called A, so we'll go for initially the block is not anywhere, so we'll go to main memory and we'll fetch the block A. From here to here, we'll place it here, and from here we'll go here A, and then core can use this block. Okay, but after some time, if it will request for the next block B, which is stored here, suppose next block B, so that block will access. Then at that time, after accessing A, then again we'll go to main memory, will fetch the block B, store it here, and then we'll store it here, right? So if somehow if we can know that okay, when core is accessing A at this moment, if we know that no, after some time core will also request for B, then when we'll send a request for A, there will be a prefetch engine here. This is called prefetch engine. So when code will request for A, that is called a demand request. Means core is requesting for A. So when core will requested for A, that request will be, or that request data will be also served to this prefetch engine, and that prefetch engine will predict that okay, after A, B will be also accessed. So it will send a prefetch request. So C1 will send a demand request for A, and this prefetch engine will send a prefetch request for B. So both requests will be reached to memory, and both this block will be moved together from memory to cache. Why? Because we're assuming that B will be accessed after A. So if this is true, then after some time when core will request for block B, then that block will be hit in the cache. So it means that somehow we can hide the huge memory latency that is required to fetch a block from main memory here. And all this thing is depend on the correct means the performance of these complete policies depend on the prediction mechanism has done means inside this prefetching engine. So in this part when we will discuss how efficiently we can design a prediction mechanism inside this prefetch engine, such that though the prefetching that is coming from here, those prefetching should be correct. Means if I am prefetching a block and storing it here, what is the chance that core will access for it? अगर core ने इसको future में access ही नहीं किया, then your prefetch the prediction is wrong. So you have prefetch incorrect data. So if you prefetch incorrect data, so you are polluting the cache, isn't it? If your prefetch is wrong, आपने B को prefetch किया and B use नहीं हुआ, इसका मतलब क्या है? So unnecessary आपने इसको B लाया, right? So in that case you polluted the cache. So that is called cache pollution. So if you propose a prefetch technique, then you have to ensure that it is not doing cache pollution. अगर cache pollution कर रहा है तो क्या होगा? Prefetch block आप लाते जाओगे, इससे हो सकता है कि demand block निकल जाए cache से, isn't it? There are some demand blocks, but they may be old, but they are demand blocks. हो सकता है कि in future core will again request for them. अभी क्या होगा? You are moving more prefetch blocks here, so those prefetch block may be may because your space in the cache is limited. Prefetch के लिए कोई अलग जगह नहीं है. So if you move more prefetch blocks in cache, according to replacement policy, आपके demand block निकल सकते हैं. And if after that your prefetch blocks are not using by the core, then it's a it's a pollution. So we'll discuss about more prefetch here. So I'm not this. So there are next line prefetch तो मैंने बता ही दिया कि if it is requesting for a block, then next block maybe we can fetch. That's called next line prefetcher. Stride prefetcher means it's follow a stride. Maybe if you are requesting a block here, then यहाँ पे जो block है वो this will be access this you prefetch this. If you are accessing a block here, maybe after whatever block is here, you prefetch that block. So that is called stride prefetcher. Maintain a fixed distance. Next line prefetcher means just prefetch the next line. So but main goal is here, there is a prefetch engine which this may in that prefetch engine all this what is can say demand request are in giving as a input, and this based on this request is predict something, and then it also send some prefetch request. And challenges in prefetching, I'm saying prefetch accuracy, prefetch pollution, learning techniques means how accurately you can predict complex application behavior. If the behavior of application is complex, if it is not following next line or stride prefetching technique means pattern, then is how to design a prefetch for them. Prefetch on different cache levels means if we want to prefetch on L2, if we want to prefetch on L1, so what are the changes required? So all these things we'll discuss when we'll discuss about prefetching. And again, we'll also discuss about security issues in prefetching, means how a person can do DOS attack on prefetching if he knows the internal logic of the prefetching. So all these things we'll discuss. But one point here you can say I've written first a special locality. Why I've written special locality? Because prefetch, if there is a successful prefetch engine you have designed, then it is getting the benefit of spatial locality. What is spatial locality says that if you are accessing a block, then it is highly likely that it will access the nearby block in future. So if there is a next line in next line prefetcher, we are just assuming this, right? If we are accessing a block, this block A, then it is highly likely the near future it will request for the nearby block B and will fetch that block. So spatial locality has a close connection with prefetching. Then the next point, that is cache utilization. So I'll not discuss much about cache utilization today because I think we have less time. But suppose we have a set associative cache here. We have a set associative cache, and there are multiple set and multiple ways. And I said that based on a particular set mapping, right? We always target to a particular set. Always target to a particular set, because if there is even if there are free space here available, you cannot map a block in this free space if the block is mapping to this set. This is the mapping policy of set associative cache. But there is a disadvantage of this mapping policy also. It may be possible that because of this strict mapping policy, this set is getting heavily used, but there are some other set which are lightly used, which are underused. So it may be, so it means that the entire cache is not utilizing properly. Unnecessary, it is giving conflict miss when you have the capacity remaining in other space. So that's why you can see I'm showing a graph here. These are the set numbers of a cache. Assume that there are how many sets here? 512 sets are here. There are 512 sets are here. Okay, and these are the number of conflict misses in each set. So you can see the conflict misses in each set are not uniform. There are some set you can see here, they are almost ideal. There are very less number of misses, but you can see there are some set where the number of misses is very high. So it means that the set are not accessing uniformly. So this is called a utilization issue inside the set. I said this is a local utilization issue, and global utilization issue is connected with TCMP. If you know this is called TCMP, right? I have explained. That's why I said try to understand the concept of TCMP again. So here, this you can see there is a, this is called a bank, right? L2 bank. So each bank is a set associative cache. So whatever I have explained here, this is true for each local bank, because each local bank is a set associative cache, and this local utilization issue is possible in each local bank. But what is called global utilization issue? Global utilization issue means this type of L2 bank, there are 16 L2 banks here, because each tile has a L2 bank, right? And as I said, in SNUCA policy, like set index, we first fix the bank based on bank index, and then we'll map the block to a particular bank, right? So in if we follow this type of index, fixed index in SNUCA, then it is also true that it may be possible that some banks will be heavily loaded and other banks are ideal. That is showing here. You can see for this TCMP I am showing here, there are 16 banks here, and it is showing the load in each bank. So you can say there are some banks which are heavily loaded, and there are some banks which are almost ideal. So it means that if you have multiple banks, then all the banks are not loaded uniformly. So ultimately, the cache space available to you are not utilizing properly, right? And that's why we are getting unnecessary misses from the cache, and which is true for both local utilization and global utilization issues. So how to handle those? How to handle local utilization issue? What are the recent technique proposed to handle local utilization issues? What are the recent techniques proposed to handle global utilization issues? All these things we'll discuss in this course. And again, the security issues of this easy security issue here is, if someone knows the internal structure of a set associative case, so वो एक ही set को target किया तो, so it can create a local utilization issue. And agar aapne, if you have proposed something to handle this, if attacker knows that counter this that hand that mechanism, what about if that attacker creates a new application to do something else? Okay, all these things we'll discuss in this course. So I think security issues of all this I have explained: repression policy, security issues, partition, cache partitioning, security issues, cache utilization, all the security issues. So in this course, there are two things. We'll understand all the concept. This is one point. Another point is, once you understand all the technical, try to find out how to attack it. behave as an attacker. Try to think that how to misuse this technique. Don't think that if you try to think in this direction you are a bad person. अगर आप नहीं सोचोगे तो कोई और सोचेगा, and maybe that person is bad. So if you at this moment you can think a possible attack, that is a very good thing. You can do your term paper on it. Why? Because we'll assume that if you find out a possible attack, another person will find out a countermeasure of that attack, right? But if you don't detect that attack, maybe a wrong person will find out the loophole and use that. So proposing an attack is not at all a bad idea. If you can find some loopholes in it, loopholes in any of this technique, you can always think about the attacks. That's why I'm giving some idea about security issues. And why it is also important. Suppose you want to propose a new replacement policy, you don't want to propose an attack. But at that moment, if you know that okay, there is a concept called DOS attack, then you may think that okay, my replacement policy should handle DOS attack also. So all these things we'll discuss in this course. So mainly today I give you idea about replacement, cache partitioning, and cache utilization. So basically these three area will cover before midsem, and if time permits we'll go to new other areas, but these three areas will cover. So from next class we'll start understanding the recent research papers. Thank you. So I'm stopping it here. So if you have any doubt you can ask now.
Hello, sir.
Hello.
Sir, can you please explain thrashing application?
Okay, thrashing application. Huh. So, in case of threshing, what I said is, suppose this is your cache and there are only 8 ways available. Eight, suppose there are only 4 way available, and you have a application here. This is your application A1 to A20. There are 20 blocks it is requesting, and after this it is again going and requesting to A1. This is how the application is requesting for block. First it will request for A1, and then it will keep on requesting till A20, and then there is a loop, and again it will start requesting from A1. So this type of, that is assume that there is a application, that is this type of application is there, and also assume that all these blocks are mapping to this set. So पहले क्या होगा, A1 यहाँ पे आएगा, then it will request for A2, so I'll place A2 here, then I'll request for A3, I'll place A3, and then I'll request for A4, so A4 यहाँ पे place हो जाएगा. इसके बाद जब when it will request starting from A5 here, then we have to replace something from the cache, because अभी cache में जगह ही नहीं है. So when application will request for A5, I have to remove this A1 and I'll place it A5 if I'm going for LRE replacement policy. When it will go for A6, मैं इसको replace करके A6, इसको replace करके A7, इसको replace करके A8, I'll do this. So it means that there is a repetition in the cache. The repetition means after A20 again I'll request for A1, but when next time you will request for A1, वो A1 अभी कैश में नहीं है, because of limited cache space, that A1 got evicted from the cache. So इससे मतलब क्या बनता है कि the application has a repeating behavior. Application में तो repeat हो रहा है. If A1 is accessing here, in future A1 will be again accessed. That is true in application. But so उसी को तो हम temporal locality बोलते हैं. But that benefit is not, we cannot get from the limited cache space. अगर 4-way associative cache है, so that benefit we cannot get from the cache. That's why it is called a trashing application. It is clear now?
Yes, sir. Thank you.
Okay. Any other doubt? Okay, so let me stop my recording here.